Normalization is a systematic approach of structuring data in a database. It is a database design approach that eliminates undesired aspects like insertion, update, and destruction of data. It splits huge tables into smaller ones and connects them with relationships. If not modularized properly, databases often provide faulty data when complex queries like joins are fired on the entities. Well, this issue can be eliminated by using normalization technique, as normalization is a theoretical concept that is implemented practically using the basic construct in a relational database management system. If you are curious to know more about the same, stay right where you are, because in this course you will explore the most commonly utilized normalization form, how they cascade onto one another, and how they help with designing a better or more modular non-faulty database. So without any further ado, let's get started right away. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.
Hello everyone. Welcome to a new course on database normalization. Now, database normalization is a term that is often heard in relation with relational databases or in relation to relational database management systems. In this particular course, we are going to be learning the hows, whys, and whats of normalization. First, we're going to understand what normalization actually is, and we're also going to look into the whys of normalization, namely, what is the requirement for normalization. Next, we're going to look at the various types of normalizations in order to understand exactly how normalization is carried out. So let's get started. So let's first look into what normalization is and why we require normalization. So normalization is actually putting up or organization of any data that we have in a database into a uniform format. Actually, what it does is that it helps us organize all the various types of data into modular formats. Now, what do we mean by modular formats? We actually mean that each and every component of the database has been arranged in such a way such that related data is clubbed together in one cohesive unit and other data is clubbed together in another cohesive unit. If these two cohesive units, normally known as entities, are related to one another, then they can be joined together using various techniques in order to actually club the data together during runtime. Thus, normalization is actually helping us in organizing data in such a manner that the data can be utilized for one or multiple purposes based upon the types of queries that you're firing to the database. Let us look at some of the other needs for normalization. First of all things, normalization reduces repetition. Repetition is also known as redundancy. Let us understand this with an example. Say we have a student table and a department or a course table. A student will obviously be a part of a department or a course. So where does the student data come in? A student data can be put into the student table, or it could be put into the department table, or the data can actually be put into both student as well as the course table. But this is repetition of data. So normalization actually helps us understand and implement a format in such a manner that the student data is being utilized with all of its related entities, but it is not repeated constantly. Next, it also helps us isolate entities such that we may be able to minimize or reduce the number of mistakes that might be cropping up. Now, these mistakes are actually called anomalies because they are not made on purpose. These anomalies actually crop up because of some permutation and combination of data that occurs whenever a join or a view or any other type of query is fired. Firing of complex queries on non-formatted or incorrectly formatted data will often lead to anomalies. We will be looking at the three types of anomalies in this course. Lastly, normalization helps us in creating more manageable modular tables. This actually means that when data which is related to each other is clubbed together in one entity, it might be used in multiple applications as it is. Since this data is modular in nature, it can be utilized for one or multiple purposes. Not only that, if there is an issue with any of the data, say anomalies, redundancy, or any other issues too, they can be easily identified and rectified. Thus, normalization helps us with redundancy reduction. It helps us with isolation such that we might minimize the anomalies that are cropping up in our database. And lastly, it helps us in creating entities and tables which are more manageable in nature. We have 5 basic types of normal forms, namely the first normal form, the second normal form, the third normal form, fourth and the fifth normal form. Apart from this, we have a variation on the third normal form, which is actually just a stricter form of it, called the Boyce code normal form. In this course, we'll be looking at all of these one after the other. So let's quickly get started. So let's look at the first normal form. The first normal form is actually the most basic normal form, and it is the initial most normal form that we need to take care of while creating the database. Let's look into the rules of the first normal form. So as per the first normal form, it is stipulated that all of the values given in it must be atomic in nature. Now, what does atomic mean? Think about your lower classes. Often, by the time we were in 6th or 7th standard, we were told that an atom was the smallest and indivisible element of matter. Now we know differently since it's been disproved and that atom is not the smallest. But the term atomic actually comes from this atom. What atomic values mean is that these values can no longer be divided into smaller values. That is what the first normal form says, that each and every value in a given table has to be of such a form that it can no longer be divided into a smaller part of itself. This actually means that each and every column that we have in a table has to hold only one particular information within itself. Let us look at this with an example. As you can see here, we have got a column for name, a column for mobile number, and a column for age. If we look at the name column, we'll see that the name consists of first name, middle name, and last name. Or in other cases, it might contain only the first and the last name. This actually causes a problem while you're retrieving data. Say for example, there is a form in which you need to fill up your name. And this particular form has stored your data in this form in the database. What happens if you want to change just your last name? You'll actually have to go and change your whole name. Insert all of it again. First name, last name, and middle name. At another instance, what if the data taken from your side is actually displayed as a hello message? So for example, here what should be displayed is hello John or hello Harry or hello Jane. But how do we extract that first name from the whole name given here? That becomes an issue. In order to resolve this particular issue, what we do is we actually split this up into this form. As you can see here, we've split the name column into 3 separate columns, namely first name, middle name, and last name. The mobile and age column remain as it is because there are just singular elements given in each of the rows. So how do we split this? Every time data is retrieved from the user, we can put in the first name in the first name column, the middle name in the middle name column, and the last name in the last name column. What happens in case there is no last name? Then we just simply add the first and the middle name. What happens if there's no middle name? Then we'll accordingly put in the first and the last name as given. So thus you can see how now it becomes easy for the system to retrieve the first, the middle or the last name as per the requirements. Thus, this is how our first normal form will be achieved. Another place that you might see this is in terms of mobile numbers or contact information. One person could have multiple mobile numbers or multiple contact numbers. All of these will have to be put up in different columns. A person should have one mobile number or contact number, but they may have multiples. So you need to apply the constraints on your columns accordingly. But a contingency needs to be made in order to ensure that all of the contact information is actually stored within your database. Similarly, you could have multiple hobbies and each hobby will have to be stored in different columns in the database. Thus, in the first normal form, we've seen that the aim is to ensure that in one column of the table, there is only one indivisible or atomic value. This means that multiple values should not exist in any particular row of any column given in the table. Next, let us look at what the second normal form is. Now, the second normal form is something that is built upon the first normal form. So first, let us look at the rules for second normal form. The first rule of second normal form states that the table that we're going to perform the second normal form on must already be in the first normal form. This is because normalization actually works in a cascaded manner. This means that all of the normalizations have to be carried forward from the previous onto the next normalization. The next rule for second normal form is stated as the non-key attributes being fully functionally dependent on the primary key attributes. Now we already know what primary key attributes are. Those are the attributes that uniquely identify the tuples of any entity. Let us understand what functionally dependent and what fully functionally dependent for that matter means. Now, functional dependency is actually a property in entities wherein non-key attributes are dependent upon key attributes for uniquely identifying them. So it is the job of the key attributes or like super keys, candidate keys, primary keys to actually uniquely identify the non-key attributes that might be there in the entity. The denotation for functional dependency is X defines Y, wherein X is the key attribute and Y is the non-key attribute. This can also be denoted or stated as Y is functionally dependent on X, saying that the non-key attribute Y is actually dependent upon the key attribute X for uniquely identifying it. This is functional dependency. Next, let us look at what full and partial functional dependencies actually mean. Now, the full functional dependency and partial functional dependency can actually be understood if we look at a table. In a table, we might have a combination of keys such that all of these keys together would uniquely identify any of the tuples. These keys or such keys are actually known as super keys. This set of keys is such that taking the combination of set of keys is actually going to uniquely identify any of the tuples given in our table. Now, this super key may have a variety of keys within it. Let's take this super key or the whole set to be D. If a non-key attribute is fully functionally dependent on D, it means that this particular non-key attribute is never going to be dependent on any of the combinations of whatever is contained within D. So what does this actually mean? It means that D or the combination of x, y, and z is the only one together which is able to uniquely identify A. This is full functional dependency. So let's understand what partial dependency is. In partial dependency, if D is able to determine A or define A, then maybe XZ could also be able to define A, or X would be able to define A, or Z would be able to define A. Therefore, what we're trying to say here is that in full functional dependency, we cannot define the non-key attribute with a subset of the key attribute. Whereas in partial dependency, the non-key attribute may also be fully defined by a subset of the key attribute. What we need in second normal form is full partial dependency. This means that no subset of the key attribute should be able to define the non-key attribute. Let us understand this with an example. Let us consider this example. Here, in this particular example, we can see that we've got the student ID and the project ID keys. So we can say that each and every tuple can be uniquely identified by the student ID and the project ID key. However, we can also see that the non-key attributes are such that they might be uniquely identified by either student ID or project ID. Let us see how. Consider first name. The first name attribute is fully functionally dependent on a student ID attribute. It's fine if it is not defined by the project key attribute. As we can see, the first name is not really dependent on the project ID attribute. This means that even though our super key is a combination of student ID and project ID, first name and for that matter age can both be uniquely identified by a subset of the super key, which is student ID. Similarly, the project name attribute, which is a non-key attribute, can be fully identified or can be fully defined by our project ID itself. Again, we can see that the subset of the super key can be used to uniquely identify a non-key attribute. Thus, this particular table is actually partially dependent. We do not need this. So how do we convert this partial dependency into full dependency? One of the simplest ways to convert this partial dependency into full dependency is actually splitting up of the table. Now, how do we split the table up? It's very simple actually. Split the table up on the basis of its functionalities. So what we do is very simple. We split the table as the student table and the project table. Thus, we can see that one single table has now been split into two separate tables. Now, if we look at these two separate tables, the non-key attributes are fully functionally dependent on the key attributes themselves. There are no other attributes here on which the non-key attributes can be dependent. Similarly, in the project table, project name, which is the non-key attribute, is completely dependent upon project ID for uniquely identifying it. Thus, we can convert any table which is not currently in second normal form into multiple tables which would then be in second normal form. Next, let's look at the third normal form and the stricter version of the third normal form, which is the Boyce code normal form. So, as we already know, normal forms cascade. So, it is an obvious conclusion that if we want the third normal form in our database, the initial table under consideration should be in second normal form already. This means that it should be in atomic values only as per the first normal form, and all of the non-key attributes must be fully functionally dependent upon the key attributes. This is what it means by the second normal form. The next stipulation here for any table to be in the third normal form is that there must be no transitive dependencies. We've already seen in the second normal form what functional dependencies are. So as a result, if we have a key attribute such that it is able to define a non-key attribute. Next, we've got, say, another attribute which is able to define a third attribute. These attributes or these dependencies will imply that the key attribute is defining the non-key attribute C. This is known as transitive dependency, and these kinds of dependencies have to be avoided in the third normal form. Let's look at this with an example. What we'll also be looking at in this example are the three anomalies, namely the insertion anomaly, the updation anomaly, and the deletion anomaly. Observe this example given here. The example is actually such that we've got a student table wherein the student's ID, the student's first name, the course that they're actually going through, the fees for that particular course, and their ages are stated. Within this particular table, we can see that everything here is atomic in nature. Apart from that, all of these values are fully functionally dependent upon the student ID. So, where are the anomalies and what is the problem here? First, let us take a look at the anomalies. Firstly, if we observe closely, here there is BMS course. If we delete the record for student 6, all the records of the BMS course would be deleted. This is known as the deletion anomaly, wherein deletion of any record from our table will lead to complete loss of that data from the table. Next, let us look at row S2 and S3. As we can see here, S2 and S3, both students have opted for the CS course. If we need to update the fees for any of these, we'll actually have to update them multiple times. Now in this example, I've given you 5 rows from which 2 are opting for the computer science stream. What if there were 500 records and there were 200 students opting for the computer science stream? This becomes extremely time consuming because the system has to actually update the records for all of these 200 fields who have selected the CS field. This is known as the updation anomaly. Lastly, let's look at the insertion anomaly. The insertion anomaly actually cannot be looked at in this particular example, but it can be understood from here. If there is a stream, say for example BMM, that is Bachelor's of Mass Media, that particular course can't be seen here. Why is that? Maybe because no student has opted for it yet. So even though the university or college may be providing that course, it won't be visible in their records because no student must have opted for it. This is known as the insertion anomaly, wherein the record will not be read or the record will not come into existence till someone or something has not utilized that particular record. Thus, we've seen the 3 anomalies that we have, namely the deletion anomaly, the updation anomaly, and the insertion anomaly. Next, let us look at what the transitivity dependency here is. So, first name is dependent upon student ID, course is dependent upon student ID, and fees is dependent upon the fees is dependent upon the course, and because the course is dependent upon the student ID, we can say that the student ID is dependent upon the fees. So that you better understand it, let me write it down. Student ID defines the course and the course defines the fees. As such, because of this particular relation, we may say that the student ID is what is defining the fees. But think about it logically for a minute. Is it possible for the student ID to define the fees? What this actually is telling you is that for each student, you could define a different fees. So you could ideally stipulate as per this particular definition that based upon the student, I may be able to change the fees. But that's not possible, is it? Here, fees is ideally dependent upon course. Whatever the course, that much will be the fees. So as you can see, IT is having a fees of 35,000, CS has a fees of 30,000, BMS has a fees of 40,000. So the course is what defines the fees and not the student ID. But in this table, that is not possible. This is what transitive dependency is. The easiest way to actually remove this transitive dependency is to split the table up. So this is how we split the table. We split the table as student ID, first name and age, and we create a complete different table for course and fees. As we can see, course name and fees are not actually able to completely uniquely identify themselves. So we introduced a new attribute here, namely the course ID. So the course ID attribute here actually behaves like the primary key, and it will now be able to uniquely identify the tuples which are present in course name and fees. So as you can see here, splitting up the table actually provided us with a better understanding of what the records are. Let's see what happens to the anomalies. Let's look at insertion anomaly. If we add a record into the table here, we would not have to add it into the student table. We could add it into the course table. This means that it does not matter whether or not a course is being opted for by a student. Till the course is offered by the university, it will be a part of the course table. This means that there is no data which is not accounted for. Next, let's look at the updation anomaly. If we need to change the fees of any course, we can simply come up to the course table and change the fees of the given course. This means that the actual updation will occur only once. For all the students who have opted for that course, these changes might be reflected later on actually performing a join or any other such complex queries. But ideally, the basic update will have to be carried out only on one tuple of the course table. Lastly, let's look at the deletion. Suppose, for example, a particular student, S6, has deleted or actually removed their admission from the university. This would lead to deletion of that particular student record from the student table. But that does not mean that just because the student has left the student table, the course would also leave the course table. Since the course is still being opted for, it will be accounted for and sustained within the course table. This is how we have eliminated both transitive dependency, and we've also eliminated the possible anomalies that could crop up here, namely the updation, the insertion, and the deletion anomalies. Next, let us look at the Boyce code normal form. The Boyce code normal form is actually just a stricter manner of implementing the third normal form. Let's look at what the rules of the Boyce code normal form are. So the first rule is, as we already know by now because of cascading, the first rule states that the tables should already be in the third normal form. This means that the value must be atomic in nature, there should be no transitive dependencies, and all of the non-key attributes must be fully functionally dependent upon the key attributes. Next, what it says here is that the non-key attributes must be fully functionally dependent upon the super key that exists within. Now, this super key, as I've already explained, is actually the set containing all of the keys that can collectively uniquely identify any tuple. Primary keys, candidate keys, etc. are actually all subsets of these super keys. Let us understand this particular concept with an example. Let's look at this particular table here. We've got the student ID, we've got the names, we've got subjects, and we've got professors, along with the ages of the students. As we can see here, the first name is dependent upon the student ID and age is also dependent upon student ID. What about professor and subject on the other hand? These two are actually not dependent upon student ID. Now in this particular table, thankfully, we've got just one attribute in our super key, which is student ID. that's denoted by s_id, right? So ideally, what Boyce code tells us is that professor and subject should also be dependent upon student ID. But here it's not. Since it's not necessary that Professor Chetan would be or should be related only to student ID S01, or that Professor Jaya would be related only to S03 student, right? On the other hand, if we look closely enough, we'll realize that the professor attribute is actually defining the subject attribute also, because this particular subject is being taught by this particular professor. As you can see, the professor key is actually defining the subject attribute. This is something that is not allowed within Boyce code normal form. What Boyce code normal form says is that subject should also be dependent upon a primary or a super key, and professor must be accordingly dependent upon a primary key or a super key in this case. So what do we do here? It's very simple. Take all of the attributes that are actually connected and related to each other, namely the student ID, the first name, and age, and club them into one entity. The rest of the columns here will go and be put into another entity. So as you can see, we've clubbed all of our attributes under consideration into two different entities. So student ID, first name, and age have been clubbed into one, since first name and age are fully functionally dependent upon the super key given here. Next, what we've done is we've clubbed professor name and student into another entity. Since there is no existing super key, we have attached a new super key or introduced a new column as a super key. That is Professor ID. Now, this particular professor is fully functionally dependent upon the Professor ID. And because it is dependent upon the Professor ID, we can say that the subject is also dependent upon the Professor ID. Because as you can see, Java can either be taught by one professor or it can be taught by a completely different professor. So the subject is no longer dependent completely upon the professor. It is actually dependent upon the professor ID. So a given professor will be able to take this particular subject and another professor would be taking another subject. That is how Boyce code normal form actually is identified. So here we've seen how we can actually reinforce the third normal form in the form of Boyce code normal form. Next, let's look at the fourth normal form. Now, the fourth normal form is a slightly more complex normal form, which is not really seen practically in many cases. We will be looking at a practical example of the same in order to understand it, but please note that normally what we look at in any particular table is the first, second, third, and Boyce code normal form. But since it's a part of our normalization, let us look at the fourth normal form also. Now, the fourth normal form is created such that it has two major stipulations. First, that the table should already be in the Boyce code normal form, and secondly, that there should be no multi-valued dependency. Now, what are multi-valued dependencies? Multi-valued dependencies are those type of dependencies where one column is dependent or defines another column, and the same column defines a third column. But the problem is that the two columns which are actually dependent upon the first are not really related to each other. So this means that A is defining B and A is also defining C, but that there is no relation between B and C here. Such dependencies are known as multi-valued dependencies because one particular column is defining multiple other columns, thereby making multiple values. This is how we actually define multi-valued dependencies. The fourth normal form says that such dependencies should not exist in any table. Let us actually understand this with a concrete example. Observe the table given here as an example. We have two students, namely S1 and S2, and they actually have been assigned to certain professors. All of these professors would recommend textbooks. So that means that the student has a particular set of professors and the student has to actually study from a particular set of textbooks. But is there any relation between textbook and professors? Even if it were a different professor, maybe the same textbook would be assigned because your curriculum or syllabus might define the stipulation. So this means that there is no correlation between the professor and the textbook being utilized. The textbook has just been assigned to the student and the students are being taught by a given professor, right? So this means that student is actually defining professors and student is also defining textbooks. But there is literally no relation between the professor and the textbook. This is a multi-valued dependency. How do we remove this dependency? We remove the dependency by splitting up the table in such a manner that only the values which are related or dependent upon one another are a part of a single entity. So this is what it looks like. As we know, student was related to professor and student was also related to the textbook. So we split up our entity in such a manner that those entities, I'll repeat that, so we split up our entity into such a manner such that those attributes which were either defining or dependent upon each other would be clubbed together into one. So student and professor are clubbed together into one and student and textbooks are clubbed together into a different entity. Again here, professor is actually dependent upon student and textbooks are fully functionally dependent upon the student. This is how we can convert any entity which is not in fourth normal form into fourth normal form. Please remember, splitting up of the table is to be in such a manner such that all the dependent values have to be put together with their key attribute and all of the rest of the values will again be repeated with the non-dependent pair. If there were name, that is first name and age here, they would also be attached with the students since they are dependent upon student. Please note that since student ID comes in both tables, name and age would also come up in both the tables. So we would ideally have student, first name, age, professor, and the other entity would be student, first name, age, textbook. This is how we can actually convert tables which are not in fourth normal form into tables which are in fourth normal form. Lastly, let's look into fifth normal form. The fifth normal form is the last most basic normal form that we have in RDBMS. Now, what is the fifth normal form? So, as we already know, for any entity to be converted into the fifth normal form, it will actually have to be in the fourth normal form. This means that the values have to be atomic. There should be complete functional dependency of the non-key attributes on the primary key. There should be no transitive dependencies. All of the non-key attributes must be fully functionally dependent upon the super key. And lastly, there should be no multi-value dependencies. That is how we get 4NF. Now, what is the extra stipulation here? That is that there should be no join dependencies if you have to actually have the entities in the fifth normal form. Now, no join dependencies is another way of saying that the entity that you finally get must be indivisible. Let us understand what join dependency actually is. When we look at joint dependency, it's a basic concept wherein if we take R as any entity or relation given in a relational database management system, then splitting up that relation into n other relations such as R1, R2, R3, etc. till Rn is possible. Now, if we club together these dependencies in the form of a join, in any manner, then we should get back the original relation. This concept is known as joint dependency. The fifth normal form states that there must be no joint dependencies within the tables. We'll look at it with an example in some time. The last stipulation of the fifth normal form is that Any and all joins that are being created using this particular table must be lossless in nature. Now let us first understand what a lossless join is. Many people feel that a lossless join is one where data is not lost. You're not wrong, but there is another condition here. A lossless join is one where data is neither lost nor is extra data gained. What does this mean? It means that if in a particular join or while performing a particular join, there is extra data being generated which was not part of the original relation, then that particular join is also called lost full. So what does lossless actually mean? What lossless means is that you should always get back meaningful data that was a part of the initial relation. This means that if there is data lost from the original relation, or if there is data which is found extra when compared to the original relation, in both cases, meaningful data has been lost in one way or the other. This kind of a join is known as a lost full or a lost join. Not having these elements in your join will actually convert it into a lossless join. Let us understand the fifth normal form with an example. We'll first look at that kind of an entity which has no fifth normal form in it, and then we'll transport ourselves to look at that kind of an entity which has the fifth normal form. Consider this particular example. As we can see, this particular example is already in fourth normal form since there are no transitivities. All of the values are dependent upon the primary key only because that is acting as the super key here too. That is acting here as a super key too. And there are no multi-value dependencies because even though student ID is what is defining professor as well as student ID is defining subject, there is a certain relation between the professor and the subject that they're taking. This means that this particular entity is already in the fourth normal form. Let us see why this particular entity is not in the fifth normal form. Let's say that this particular relation is R, and I'm going to split this relation R into three separate relations, namely R1, R2, and R3. So here we have relations R1, R2, and R3. Taking a join of R1, R2, and R3, we realize that irrespective of what combination of join is taken here, we will always get back the exact same relation R. Let us take an example of that. Suppose we take up Professor Chetan here. Professor Chetan is teaching the subject C++, and C++ is something that has been opted for by S01. So student S01 is taking Professor Chetan's class, which is for C++. So taking just the join of R2 and R3, we are able to obtain the whole tuple that was a part of R. The same can be said for each and every record that is a part of the tables R2 and R3. Let us take an example of R1 joining with R2. If we consider student S1, or let us consider student S3. Student S3 is currently working under Professor Jaya. Professor Jaya teaches C#. This means that S3 should ideally be learning C# from Professor Jaya. This is an actual tuple that is present as a part of the original relation. So as you can see, both of these joins are actually giving us back the original relation. Let us take the join R1, R2, and R3. Again, we can see that if we take S5, student S5 is actually studying under Professor Tara. Professor Tara is concerned with TOC, and TOC is something that is taken by student S5. Again, what we get as the result is that we've got our row 5. As a result, we can see that any combination of joins that are taken up for the sub-relations here will give us back the original relation. The concept actually being displayed here is joint dependency. And we know after looking at the stipulations of the fifth normal form that joint dependency should not be inherent if we've got the fifth normal form. This implies that this particular table is not in the fifth normal form, since it can be split up into three separate relations, and all of these relations in join does provide us back with the original relation. So it is not in the fifth normal form. Now look at the next example. Again, this is a table which is already in fourth normal form. We need to test whether this particular table is in the fifth normal form or not. Consider that this table is the relation R, and we are splitting this table up into three separate tables, namely R1, R2 and R3. So these are our tables R1, R2 and R3. Let us consider an example wherein we are creating a join between R1, R2 and R3. Let us take an example of student S2. Student S2 is currently learning under Professor Javed. Professor Javed is currently teaching Java. Student S2 is currently taking Java. This is actually a part of the original relation where student S2 is taking Java under the tutelage of Professor Javed. What is the problem here? The problem comes up in this particular section. Consider the exact same value for relation R1. Student S2 under the tutelage of Professor Javed. Coming up to relation R2, we have another Professor Javed here teaching subject DS. It would obviously be the exact same professor. And DS is being taken up by student 4. Can you see the anomaly that just popped up here? We've got student S2 who has started it, and then we end up with student S4. This does not make sense, does it? Because where did student S2 go? There is no record actually defining all of this. Let's take another example. Let us take R1 and R2 in a join with each other. Let us take the exact same example as before. S02, who is under the tutelage of Professor Javed. When we look at relation 2, we can see that Professor Javed could either be teaching Java or Professor Javed could be teaching DS, data structures, right? So we are actually getting another record that student S2 is actually under the tutelage of Professor Javed and is actually studying data structures. This particular relation exists in our original relation, but this particular tuple does not exist. So this is something extra. As we've already seen initially, extra data also becomes a part of lossy data. Thus here, we can't really take up the relation and split it into parts and then get back the relation while we're trying to join the various parts of it. This means that there is no join dependency. This means that this particular relation could potentially be in the fifth normal form. Now, please note that the fifth normal form is mostly taken up as a theoretical concept and not really implemented in the practical world. This is because this particular normal form does not come into being till the database is not in runtime. 90% of the time, if you've created your tables in the proper manner till Boyce code normal form, the fourth and the fifth normal form would never be seen. This means that if a database has been properly created in such a way that we have incorporated 1, 2, 3 and Boyce code normal form, then we would not really be seeing the fourth or the fifth normal form's anomalies within them. The fifth and fourth normal form are mostly taken up as theoretical in nature, but in certain cases, they would have to be implemented. So this is how we can get the fifth normal form. So let us quickly summarize what we've seen in the entire session. Firstly, we've looked at what normalization is, wherein we've seen that it is actually a form of applying uniformity to any given database. Right? Next, we've looked at why we require it. So, as we see in school uniforms, any changes, any lacuna, any limitations that are there in the data will easily be accessed and can then be removed from the database. Not only that, we are also able to see all of the redundancies that may be a part of the database and eliminate those. So, format, redundancy, and anomaly minimization. Next, we've seen what the first normal form is. So we know the first normal form has to be atomic in nature, wherein one particular column in any of its tuples should have only one indivisible value given. Next, we've seen the second normal form, which has two stipulations. Firstly, the table has to be in first normal form. And secondly, that the non-key attributes have to be fully functionally dependent upon the primary key attribute. Next, we went on to see the third normal form that actually states that any entity which is in the third normal form has to be in the second normal form first, and that no transitive dependencies must exist within the entity. Thus, if you have second normal form and no transitive dependencies, we will get the third normal form. Next, we've got the Boyce code normal form, which is a stricter form of the third normal form. Here it says that the entity must initially be in the third normal form, and next that any non-key attribute must be fully functionally dependent upon the complete superkey attribute. Next, we've got the fourth normal form, which stipulates that the entity should initially be in the Boyce code normal form and that no multi-valued dependencies must exist. Right? Lastly, we looked at the fifth normal form, wherein the stipulation is that the tables should be in the fourth normal form and that there should be no join dependencies. A stipulation that was also carried out there was that any joins that you make later on should be lossless in nature. Thus, we've seen what normalization is, why we required it, and what the various types of normalizations are. Thank you so much for attending this session.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.